I think it's, we should just start and maybe hopefully the people will turn up. Okay? Okay. I thank everybody for being here. It's a special day. We have a wonderful guest all the way from Italy. And you know, Italy is known not only for pizza and what else, pasta, but there's Michelangelo, there is Galileo, great scientists and artists. And we have the next great architect of neural network and artificial intelligence. We have all the way from the best university, a university that has a history of 800 years. University of Sapienza. Sapienza. Sorry about this. That says a lot about my intelligence. University, and it's in Rome. 800 years, the best university in Italy, and one of the best and up-and-coming scientists for artificial intelligence. And today, I think he's going to talk about neural networks. I think it was a hypernet.
Hypercomplex
network that he's going to talk about. Let me just say a little bit about Professor Danilo.
Comminiello.
So it's just, yeah. And his research interest is in design analysis of modern artificial intelligence, including neural network and deep learning, and generative models, and adaptive learning. And he's a senior member of IEEE, and he is actually my boss in the society. He tells me various things to do for the society, and I have to do it. And he will be the chair next year, right?
It's not sure.
For machine learning for signal processing technical community, and it's an absolute great pleasure to have him here. I think it's his first visit to Korea, and he has brought his wonderful colleague, also from the same university and department. And he's also written a book on adaptive learning methods. And I think it will be a great learning experience for us to have him give us this wonderful talk. Let's give him a warm applause and let's welcome him.
Thank you so much. Thank you, Professor Murillo, for this introduction. Thank you so much for this introduction. I'm very, very proud to be here, and I hope you enjoyed the talk. So before starting, let me say, stop me whenever you want if you have questions or any doubts, or if you don't catch anything, just stop me and ask me to repeat. Is this for Mac? No. Yeah,
Oh, we saw the screen before. What happened?
Yeah, the screen works.
Oh, you're
Okay,
good.
okay.
Sapienza.
Okay, so today I would like to talk about hypercomplex deep learning. Every one of you ever heard about hypercomplex, the word hypercomplex? Do you know what is hypercomplex? Yes, this is good because I'm here to demystifying the hypercomplex, because it is actually a word which is not easy to deal with, because it deals with complexity and hypercomplexity, so it is something that is not easy to deal with. But actually, I would like to show you that it is something that can help you and also simplify things when we build neural networks. So in my presentation, I would like to introduce very briefly what are hypercomplex algebras. Then I would like also to show how to exploit hypercomplex algebra and develop some learning algorithms in the hypercomplex domain. We'd like to show some property of correlation in the hypercomplex domain. Explain very briefly some inductive bias in the hypercomplex domain, so some properties that can be exploited for neural networks in order to have great performance, and also something to go beyond hypercomplex algebra, and finally some examples of application that can be also of general interest. So I will start soon just introducing the Cayley-Dixon and hypercomplex algebras. So why do we need hypercomplex domain? So what is the hypercomplex domain? Hypercomplex domain is nothing but an extension of the complex domain. So we have the real value domain, the complex value. The hypercomplex is just an extension in which we have other imaginary units. Why do we need hypercomplex domain? Because actually in our world we have a lot of unstructured data that we need to use a lot of deep learning models, and very often there are a lot of 3D or also multidimensional data, and so this is one of the main reasons why we need some kind of hypercomplex model. We want also to optimize some kind of geometrical properties like rotation, translations, and also for having some kind of properties like invariance, equivariance, and so on. We can have also some complexity of large-scale neural architectures, because we are implementing very, very huge networks. So it is very using hypercomplex domain, we can also reduce the complexity of some models. So the advantages, I would like to start soon exploiting the advantages of hypercomplex domain. So data can be processed in the domain they reside. So this means that if you have some data in a three-dimensional space or in a multidimensional space, we can directly process data in their domain. The multidimensional highly correlated nature of input signal is exploited. So we want to exploit as much as possible the nature of the signals. Neural computation are redefined in using some kind of properties of hypercomplex algebra. This leads to a significant reduction of network parameters. And also hypercomplex models capture spatial correlations and also patterns inside the data. There are a wide variety of applications in which we can apply hypercomplex neural networks, and so we can go from images to airspace application, robotics, audio signals, graph, and so we have a wide variety of applications. basically, the fact is that we want to exploit, we want to analyze multidimensional signals. I would like to start, so what is an hypercomplex number? So hypercomplex number is defined as an element of finite dimensional unit algebra, but not necessarily associative or commutative over the field of real number. So it is something that extends the real value domain, the complex value domain, but it may have some different properties. So hypercomplex number denotes a family of number systems, and it may include a lot of algebras like quaternions, and also quaternions and so on, tesserates, octonions, and so on. So it is a huge family of, there are also a lot of algebras that go beyond complex value. So hypercomplex algebra was introduced in the late 19th centuries, and it is the basis of some modern group representation theory, which is also very used in a lot of computer vision application and so on. So basically, it is something that is it is a mixture of the real and Clifford algebra and the Cayley-Dickinson algebras, which define some properties. So the Cayley-Dickinson algebras can be distinguished based on the dimensionality of the order. So basically, we start with an assumption, a very tight constraint from the Cayley-Dickinson algebras, which is nothing but having the dimensionality of the data, which is equal to 2 to the m. Based on this equation, we can derive different algebras. So, for instance, complex value domain, just by having the dimensionality equal to 2. Quaternion domain tesserating for a dimensionality of n equal to 4, octonions for n equal to 8, sedonions equal to 16, and so on. So there are several possibilities. We need to consider that everything is, every algebra follows this constraint. So it is a power of 2, it's a base of 2 of this Cayley-Dickinson equation. Why it is good to have hypercomplex algebra to represent multidimensional signal? Because a multidimensional signal can have a dimensionality that can vary depending on the signal, the application, and so on. But we can represent in a unique hypercomplex signal a kind of different dimensionality of a multidimensional signal. So basically we can, so these numbers are nothing but the imaginary units, so like the complex domain, but in the complex domain we have just one imaginary unit, so in the hypercomplex we can have a number n of imaginary units. So for each dimensionality, so for each element, we can associate a real valued component, which is nothing but a dimensionality of the input signal. So we can represent, in a single entity, we can represent a multidimensional input just by dividing each dimensionality in a hypercomplex imaginary unit. So apart from let me say, elegant representation, we have some very good properties when we move to learning, and I will show you. There are some difference, of course, in having n equal to 4, 8, and so on. We can say that if m, so if m is greater than 2, we can have algebra of dimensionality at least equal to 4 that are non-commutative. So when we move from complex domain to the quaternion, for instance, which is the order 4, we lose the commutativity property in the algebra. This means that when we take multiplications, we don't have the commutativity in the multiplication, and we need to pay attention. and so on. So when you go up in the dimensionality, we lose other properties like associative, or we cannot have zero divisions for pseudonyms and so on. So we can say that each time m increases, so each time also the dimensionality increases, we lose some kind of algebraic symmetry. And it is very important because we need to redefine some kind of operation accordingly. Quaternions is basically the most popular hypercomplex algebras, and it is the algebra based on 4 dimensionality, so 1 real part and 3 imaginary units. And it was created was introduced by Sir William Rowan Hamilton, and it was a great mathematician, and it provides lots of properties of quaternion algebras, and we can write the quaternion algebra in this way. So a quaternion number, or also you can extend to signals. A quaternion signal, it is just based on 1 real part and 3 imaginary components. And basically you can associate to each component, you can associate 1 dimensionality of your dimensional signal. So it is very, very good to process 3D or 4D signals. Of course, we lose the commutativity of the multiplication, so we need to consider that each time we have the multiplication of 2 axes, so multiplying 2 axes is not the same of having the inverse. So we need to pay attention. How to pay attention to this fact it is just in the redefinition of the multiplication. So based on this non-commutativity, we need to redefine the multiplication, and this means that we have some kind of table in which we just basically associate the multiplication between axes and components. So I don't want to bore you too much with the mathematical stuff, but just to say that we have a redefinition of the product, and this kind of product is called the Hamilton product, and it is at the base of the success of hypercomplex model applied to neural networks. We can have a lot of mathematical and algebraic properties, for instance 3D rotations. Why? Because we can perform 3D rotations very easily in their domain, because we are just analyzing with Hamilton product in a 3D space, and so we can just just using multiplication, we can apply very easily rotation in 3D space. And also we can have other properties like involution, which is just a mapping of its own inverse or self-inverse mapping. So I would like to show how to exploit this kind of algebra for learning process, and why it is so advantageous. So basically, hypercomplex neural network allow to reduce the number of parameters by sharing blocks of parameters based on the multiplication rules. So we saw how to redefine the multiplication rule for quaternions. Of course, each algebra has its own redefinition of the multiplication, but the quaternion one is the most popular algebra. So based on this fact, hypercomplex process, neural network processing of channels as a single entity, and by this fact and sharing some parameter, they are able to grasp internal latent information without adding any additional extra information, and basically they exploit the algebraic multiplication properties. So this is basically a workflow of hypercomplex deep learning. So We start with our multidimensional signal, which can be, for instance, I don't know, some sensor signals, or also an image, because we can also consider the RGB channels as the dimensionality of the input. So I don't know if you work with images or if you work with audio, it's very easy to think to this kind of situation. So basically we have the first, it is not basically a precursor, but just a channel splitting, in the sense that I take the first dimensionality and I put it in the embedding the one of the components and so on. So we have this channel splitting, and then I have the embedding in the hypercomplex domain. So basically I built the signal in this way. So I build the signal in this way. So I put each component in every part of the hypercomplex axis, and then I build the hypercomplex embedding of the input signal. Then once I have the formulation, once I embedded the signals in a hypercomplex signal, I can use some kind of hypercomplex deep learning model. Based on this model, we can then have some kind of output. Okay, so basically you can say that this part is very easy to think, so it is just a composition of the hypercomplex signal. And here you can find hypercomplex models. So how to build a hypercomplex model? You can use any kind of deep learning model, neural network and so on, and just change the multiplication rule with the Hamilton product. So just by changing this product, you can build quaternion deep learning model, or hypercomplex if you want to extend it. We need some kind of rules. We need some kind of rules because relational rules deeply affect the definition of learning operations. So learning layers are defined for as elements of the hypercomplex domain. So basically, as said, we can have operations of multiplication, convolution, and also, of course, attention and other kind of similar operations that are redefined in the hypercomplex domain. So they obey some domain-specific rule. So these are some kind of specific algebraic redefinition of multiplication. We basically saw the quaternion ones before, but you can have also some kind of other, depending on the algebra. If you increase the dimensionality, you need to redefine the algebra, but of course it depends on the kind of algebra you want to use. So I would like to just very briefly show how to compose a layer, a hypercomplex layer. So for instance, the hypercomplex fully connected layers, they are defined similarly to a real value domain, but this kind of multiplication is performed by the Hamilton product. Here you, like in the complex value domain, you cannot have a global split activation function, but you need to have a split activation function, in the sense that you can apply the activation function to each component. And also similarly, you can define the convolution operation for a convolutional neural network. So it is just a redefinition of the multiplication if you consider the table we saw some slides before. So of course it is a little bit more complex than before. It is just some kind of mixture of input signal and weight, parts of the weight matrix. So basically we have some kind of representation. So it is a classic inner product in real value fully connected layers, in which each input neuron is connected to each output neuron. Okay, so we have, imagine that we have a matrix, a weight matrix of 16 elements. Of course, we need to consider all the elements. What happened in the quaternion fully connected layer, that we don't have all the connection, but based on the definition of the Hamilton product, we have just 4 components. And we have also 4 parameters that are shared in the weight matrix. And basically this composition is nothing but the composition of the Hamilton product that we have. So basically we have that instead of using 16 parameters, for instance, in this example, instead of using 16 parameters for the weight matrix, I just use 4 parameters. And I share the parameters, I compose the weight matrix just sharing the parameters. Okay, so this is a great advantage of quaternion in this case, because we have a significant reduction of the parameters. And most of all, the fact of sharing this parameter associated to the fact that you are processing multidimensional input signal that probably are correlated in some way. This also helps grasping latent information related to the signal you are processing. So it is an example of image processing by a quaternion network. So for instance, you have RGB channels, and so you, with a real valued neural network, you can just concatenate the channels and apply a convolutional neural network. Here you can embed the image in a quaternion, and then you can apply a quaternion convolutional neural network, in which the only thing that changes is that the convolution is redefined based on the Hamilton product. And similarly, you can define attention layers in the same way, so if you want to use transformers and so on. Or you can define graph convolutional layers if you are dealing with graph neural networks. What is important is the fact that we have intrinsic correlation in multidimensional signals. So actually, in particular, we can have some kind of capturing 2 important aspects, which are inter-channel and intra-channel correlations. That is something that can be grasped more with respect to the real-valued networks. So in particular, so we want to focus on these 2 components, these 2 aspects. So intra-channel correlation is something that also can have with using real-valued neural networks, in the sense that we can we want to understand the relationship between the same channels across different layers of the network. So I just focus on individual channels, and I want to basically understand the propagation of the information over the network. So this kind of information is related to to grasp the global features. So we want to understand the global features. It is like having a low-pass filter in the Hypercomplex layer that highlights. So, for instance, if you process images, global features just give you the shape or curvature or something like this. So something that can be smoothed by layer by layer. On the other hand, we can have inter-channel correlation, and it is possible by using and interpolating also information just by applying the Hamilton product. And so in this case, we can understand local features. So it is like having a high-pass filter. So basically, we can have information that are similar among different channels. it is just a representation. So basically, we can have, for each channel, we can have some intra-channel correlation due to the fact that we are propagating the information over the layer, and it is just a low-pass filtering of the information. Or you can have some kind of inter-channel information in which you can understand, just by the shared weights, you can understand some kind of patterns that are similar among the channels. So you have two levels of correlation, and you can explore, you can exploit this kind of correlation with hypercomplex neural networks. So this kind of feature promote inductive bias. So of course, if you know this kind of information, we can say that, okay, we have an advantage in having the process of multidimensional signal with this kind of network. So having the process of multidimensional signal, which can have this kind of correlation, is an advantage, is some kind of good property, which is nothing but an inductive bias, like we have inductive bias for a convolutional neural network, like locality and translation invariance, for instance. So I would like to talk a little bit about, more in detail, about the inductive bias for hypercomplex deep learning, just to let you understand what are the advantages that we can have using these methods. So basically, okay, the role of inductive bias in deep learning is well known. What is the inductive bias? Just a set of theoretical assumptions. So they provide a clear explanation of why some kind of model may bring some impressive results. And so you can also focus the learning arguing to prioritize one solution over another one. So if you have some prior knowledge, you can exploit some prior knowledge. Also, inductive bias may be distinguished as relational and non-relational assumptions. Basically, relational assumption focus on relationship and interaction between different entities within the data. So basically, just to understand what are the interaction inside the data. And they are inside a neural network architecture. They involve the connectivity of neurons, topological architecture, social networks, knowledge base, and so on. They also facilitate high-level cognition, reasoning, and inference. So relational inductive biases are very known in neural networks. So for instance, we can have, of course we don't have any inductive bias for fully connected layer because we are just using all the connection, so we don't have any relation. But for instance, in convolutional neural network, we can have some locality, and so we can have some spatial translation invariance, but we can have also in recurrent neural networks some sequentiality that can be exploited. In the same way, we have some relation on the edges for graph neural networks. So we can have a neural network that basically became famous, also became popular also due to their properties and on this kind of relation that they can have. Non-relational inductive bias are basically some biases that can transform similar representation without affecting the relationship between signals. So basically, we can talk about activation function, regularization terms, dropout, batch normalization, and other similar operations. How to move from a real value inductive bias to hypercomplex one? So basically, in hypercomplex neural networks, we have mostly the same inductive biases that we have in the real value domain, but we can have something more related to the fact that we already saw. So basically we have a dimensionality bias, which is related to the fact that we are exploiting the multidimensionality of the input, some algebraic bias due to the fact that we are exploiting the algebraic properties, and so we have other geometric related biases and also some regularization. So for dimensionality bias, we already saw some kind of information. So basically we can exploit global features like spatial coherence, temporal dependencies, and so on. But we can have also some kind of dimensionality bias also potentially lead to more expressive and nuances representation, because we can have a compact representation of signals. So it is something that, of course, if we have just if we don't have multidimensional signals, we cannot exploit hypercomplex models unless we have some kind of transformation of the input signal. We will see some examples before. But of course the multidimensional aspect of the input signals is very important. The algebraic bias is basically due to the fact that we have specific algebraic assumptions like the non-commutativity in the quaternion domain, and we have, for instance, the Hamilton product. So basically we have the sharing of the parameters inside each weight matrix for each layer. And also we can have, apart from the quaternion, we can have other algebraic bias for Octonion deep learning if we want to consider dimensionality of equal to 8, in which we need to redefine the multiplication considering the non-associativity. Also in Clifford algebra. So basically we can have some benefits. So basically the algebraic biases provide deep learning models with a unique way to capture interaction and patterns. As challenges, we can require careful attention when designing network and learning algorithms. So we need to consider that a priori we need to redefine the product. Geometric biases are also very important, that we saw initially. So, for instance, in the quaternion domain, we have some very good properties of 3D rotations, and so we can explore this kind of properties like rotation, translation, and so on. And so we can build quaternion neural networks that can be very, very powerful to implement operations like 3D rotations, but also some kind of translations by using dual quaternion, which is just another variant of the quaternion. We can have also some kind of invariances, so basically we can have geometric invariants, so basically in application like object detection, topological deep learning. We can have scale invariants based on object detection, image classification, perspective invariants, color invariants if you are dealing with image processing, computer vision, representation invariants, and so on. So basically this can be applied directly in the hypercomplex domain. So imagine that you are dealing with data which are embedded in the hypercomplex domain. So you can imagine them exactly on a sphere, for instance, if we are talking about quaternion. So it is very easy also to deal with this kind of invariances just by changing the axis you want to consider. And also you can have something like, similarly you can have equivariance properties like rotation equivariance or translation equivariance. So it is a very simple example of the rotation, the equivariance in models. So we have a Lorentz system, so basically we have the original set, and we can have the original set, and we can say that in the first row we have the translation. We can have also the rotation and the translation, so we can see that in the real value domain we can have something that is able to deal with rotation, but not exactly. Also with quaternion we are more able to deal with rotation, but for instance with dual quaternion we are very able to deal with rotation because we are exploiting some kind of additional properties of dual quaternion algebra. And also it's the same for translation. So for the translation real value, then quaternion may have some problem, while dual quaternion is very perfect in also capture the translation. And it is able to, so for instance dual quaternion has this property to include the rotation equivariance and the translation equivariance the same simultaneously. And so we can have just as a final bias, we can have the regularization bias, but it is nothing but, so apart from applying some regularization bias like non-relational, like penalty terms, data augmentation and so on, we have an intrinsic regularization bias that is due to the fact that the Hamilton product shares some parameters, so we can have some kind of reduction of parameters. So if we have very large network with a lot of parameters, we have some kind of reduction of the parameters that can guarantee some kind of reduction of the overfitting. And so basically also hypercomplex neural networks are also more robust in that sense with respect to large models. So it is very good to experience this kind of phenomena when networks are very, very large. We can also go beyond our complex algebra. So, okay, we have seen that we have hypercomplex may have n equal to what we want to imagine, but how to go beyond? So how to go beyond? The only way to go beyond is to address some kind of limitations that we can have. And basically the strong limitation is the fact that we have some domain-specific inductive bias. So basically the only limitation is in the Cayley-Dixon construction in the equations that we saw initially. So basically this is the constraint we have. So actually we can move from a dimensionality of 2, then 4, 8, 16 and so on, but we cannot have other kind of intermediate dimensionality. Okay, so we want to go beyond and try to overcome this limitation. How to do that? Just by considering some kind of parameterization of the hypercomplex algebra. We can have some parameterization of hypercomplex algebra. So basically we want just to express the Hamilton product as a product of a Kronecker product. So basically we can represent this matrix, which is the matrix I achieved by the Hamilton product, in terms of addition of 4 Kronecker products. Okay, so basically we have just some kind of fixed matrix that encode the algebra rule. So in this case the hypercomplex, the Hamilton product. So we know that we have some kind of fixed position for each element. And then we have the filters of the convolution or arbitrary operation that we want to consider that are multiplied, and so basically spread over the matrix. Okay, so in that way. So decomposing the matrix in this way allows us also, of course, we can consider parameter reduction of 1 over n. Composing a matrix like in this way also leads us to the fact that we can also consider, for instance, a dimensionality of 3, and just removing one of these terms, and also adapt these other matrices in order to, let me say, grasp the algebra rules. Of course, we are not talking of a very well-defined closed algebra, but we are basically losing some kind of algebraic properties, but we are exploiting some kind of biases that we can have from hypercomplex domain. Basically, those ones are related to the Hamilton product and the dimensionality. So, for instance, we saw before that if we want to exploit, if we want to process an image, an RGB image with a quaternion, we need to put a 0 in the real part, and we need to put RGB in the 3 imaginary units. In this way, we can directly process in the dimensionality of the input signal. So basically, we consider directly a dimensionality of 3 for an RGB image. We can reduce further the number of parameters, but we can have some kind of process in the domain the data reside. And so even in this way, we basically exploit dimensionality bias because we are focusing on the exact dimensionality of the data, on the algebraic bias because we are basically exploit the Hamilton-like product. So even if we go to a different algebraic, we are not related to a specific algebraic domain, but we are just exploit the composition of the algebraic of the Hamilton product, basically the resharing of the parameters. But we are learning how to share what is the exact position of the shared parameters. Of course, we can have the regularization rule, and with respect to the geometric related bias, we can have some loss of domain-specific biases, for instance, imbias and equivariance biases. So if you are interested in focus and exploiting too much these rules, basically these properties, you can go with the parameterized hypercomplex, but if you are dealing with geometric properties like equivariance, translation invariance, and so on, it is better to consider a fixed hypercomplex algebra rule. And just to close, I would like to show you some examples because basically you can also understand all the possibilities that you can have for these kind of models. So basically you can have different applications, and of course for different applications you can apply different biases. You can have two main approaches. You can leverage the dimensionality bias by embedding multidimensional signal on hypercomplex axes, so the examples that we saw before. Or you can also leverage some geometric related biases, and you can basically exploit a low dimensional latent space in the hypercomplex domain. So basically you perform some kind of transformation in the latent space, and then you are embedding the latent space in the hypercomplex domain. And I think it is a new way that will be explored in the next years. So for instance, if you deal with image analysis, of course, as we saw, these kind of models are very, very well related to images, and so you can exploit a lot of bias, especially the dimensionality bias for color image channels, of course, but you can also exploit algebraic and geometric and regularization bias. You can have also some kind of improvement with parameterized hypercomplex network. So it is an example of an hypercomplex ResNet on Cypher 10, and we saw that basically for image classification, using an hypercomplex model, we can go also beyond the performance of the real valued networks, but also quaternion on well-defined properties. So if you are interested in this kind of application, it is better to use some kind of parameterization like this one. You can have also some kind of image synthesis, so generation of images, because at the end the thing that is important is the data. So with the data, if you can find some good relation with images, then you can apply image classification, segmentation, every kind of task you want, and also image generation. So for instance, we can have like image-to-image translation task. This is a model that we developed some time ago, and it is nothing but a kind of style gun that is based on quaternion products, quaternion Hamilton product, and at the end we can have some good results also for this kind of image-to-image translation. So also with generation of data, we can include hypercomplex model, quaternion and hypercomplex models. We can also exploit hypercomplex neural networks for 3D audio. Also 3D audio, for instance, so in particular quaternion neural networks are very well suited for ambisonics 3D audio. What is the ambisonics? Is a kind of microphone in which you have 4 capsules, but they are in the same point, ideally in the same point. So you have a capsule, a microphone capsule, which is an omnidirectional one, and then you have some kind of 3 capsules that are of, so basically the omnidirectional one capture the pressure, the sound pressure, and the other microphone, which are bidirectional microphone, capture the velocity, so basically the movement in the environment of the audio. So the important fact is that we can, as the ambisonic is a microphone which is considered as a single microphone, but it contains 4 different microphone capsules, we can use the same for the quaternion. So we can encapsulate each signal in a quaternion component. So basically we can consider the directional signal as a real component of quaternion, and the other 3 parts as the imaginary part, and so we can have a very, very nice process, because we can deal very easily with this kind of process. But we can also extend and use also, I don't know, dual microphones, and also considering dual quaternions for amplitude and phase and so on. So you have a lot of possibilities. Also, we can apply to some kind of speech emotion recognition. We applied also quaternions to speech emotion recognition. It is a little bit different, because we applied quaternion models to monaural speech signals. So in this way it is easy to understand, because you have the natural representation of this signal. In this other way it is a little bit different, because you are processing a monaural signal. So basically what we did is basically to transform the signal in the emotion components, and basically valence, arousal and dominance. And so basically we work in the emotion space by considering each component as a component of quaternion, and then we have some kind of rotation and translation in the hypercomplex latent space and also we can have some kind of good properties like invariance and equivariance, and we were able to perform speech recognition, speech emotion recognition in this way, in a very easy way. So once you define the multiplication, it is like having using a different layer, so another layer with respect to the real valued ones. Also, it is very, very nice to apply this method to multimodal and multi-view image analysis, and for instance we applied in a lot of things also in medical images, in which you have both multimodal and multi-view. So for instance, for breast cancer screening, we applied hypercomplex model, because in this problem you have that you have 4 images, and then you have ipsilateral view and bilateral views, and basically if you, so a clinician basically when want to perform an analysis, just read the 4 images together, okay, and then a clinician can say, okay, there is a cancer or not, for instance. So we want to mimic this kind of reading process just by analyzing for the multi-view for in the hypercomplex domain. So basically we want to exploit global and local features. So global features in this case are nothing but the shape of the images with the propagation that the information that is propagated through the layers, while the local relations are nothing but the relations that we can have among the views. In this way we can associate very easily some kind of global relation. In this case the shape is very decisive also in understanding if there is some kind of pathology, but also of course some kind of intra-channel correlation are very good to understand if there is some kind of things to be to pay attention to. And this is a kind of network we used. Basically we have 2 views, or left views and right views. Then we have a shared encoder and a classifier. So each kind of things, each kind of multiplication inside this architecture is based on Hamilton product. And so this is a kind of representation of the results. So basically if you consider a real valued network, you have some kind of situation like this one. So it is just a representation of, this is the ground truth basically. So you have 2 kind of nodules to pay attention, and basically if you have the 2 views you cannot have complete. So basically using a real valued network you can just detect one of the 2, while if you have the hypercomplex models you are able to detect both the nodules in the single image. And so we also have other tests like this one. Another kind of very nice things is for pose estimation. We use the dual quaternion networks, in which we saw before we can exploit both the rotation equivariance and the translation equivariance. And like the Lorentz system, we exploit this particular tract also to pose estimation. And we can say that based on the ground truth, we compared some real models, quaternion, that are able to catch the rotation but not the translation, while basically the dual quaternion are deal with capture both the rotation and the translation together, and they are very powerful in that sense. Okay, I have also other application, but I think I bored you too much. So to conclude, just to say that we have some great advantages of using hypercomplex neural networks, like a reduction of the parameters. we are able to generalize models with respect to unknown data. We can have compact representation of signals in the single hypercomplex entities, and we can perform transformation in a higher dimensional space. As a future work, we can think that it will be very interesting to apply, to exploit the approach in which hypercomplex latent space are embedded with respect to the input. So in this way you can also apply these models also to other kind of signals, not only multidimensional. We can derive verify inductive bias also for different hypercomplex model and application, and based on this fact we can also develop new hypercomplex models focused and targeted on some specific task, and also it is very nice to describe and try to exploit the intrinsic physical process of signals that we can process. So these are some references that I used in this paper, so thank you so much for the attention and for being here. It is a very pleasure for me to be here.
Let me.
Yes.
Well, you know, this just confirms, it's a wonderful talk. This confirms that Italians are geniuses. You know, I've visited Venice and Florence. They have always introduced magnificence and elegance into this world, and you're here to introduce this magnificent and elegant hypercomplexity into deep learning. It's amazing. I really think it's first time I've seen something like this. I'm thinking there's a couple of questions. I mean, you've mentioned inductive bias. Okay, I think this inductive bias can be very interesting when you have few data. So when you have a lot of data, maybe you want to have a lot more freedom in the design of the deep neural network. But when you have a small number of data and you want to create something very magnificent, then this inductive bias can be very helpful. And I'm just wondering how much, you know, this is it's a sort of a field where you can have 4 levels, you know, quadrillion, then you have octillion, those words. It's a powers of 2, right? How much of a saving in terms of data do you get in terms of, let's say you're looking for accuracy, or let's say if you are generating something, how much in maintaining fidelity, FID, let's say, for instance, by introducing more inductive bias. Inductive bias. I think that would be sort of, so that was one of the questions. And another thing is the statistical properties as you go into higher dimensions. I mean, you've mentioned that there is a lot of correlation as you go into higher dimensions, and I can see that that would bring robustness. But in terms of statistics, what's sort of thing that you would expect to gain?
Okay, so I try to reply. So with respect to inductive bias, I think that it is true. So we experience also, we use this kind of quaternion models also for adaptive filters with very few data to be processed. Actually, when we use this kind of networks, we can see that basically if you don't have if you don't have some specific bias and you use a hypercomplex model, you can have more or less the same accuracy, maybe something less in some cases, and so it is one of the things that discourage also research in using hypercomplex model, because if you use this kind of models but at the end you have the same accuracy of real valued one, okay, it has no particular advantages. On the other hand, you need to consider that you always have some kind of advantage in terms of computational properties, because you have a significant reduction of the overall parameter in the network. But of course, if you use a small number of data, probably you don't need a large number of parameters. So in that case, it is not very. You need some kind of inductive bias in order to exploit at best this kind of models. And for instance, the dimensionality is very, very important. For instance, in the case of 3D audio, that kind of modeling of the physical phenomena, it is very important, because you can you can represent that kind of behavior in the same way, in a similar way, and this kind of bias can also be very powerful also in having results, for instance, in the audio signal processing. While it is different for image classification, in which maybe you cannot have the same results. If you increase the data and if you move to large networks, of course, so there is a range in which you don't have any kind of advantages for inductive bias. But when you go to very, very large models, also inductive bias has some sense, because you can have some kind of I don't know, a sharing of the parameters and some kind of regularization effect which is implicit in the Hamilton product. And this fact can also naturally regularize your model, and so prevent some kind of overfitting. So it is basically some kind of regularization that you can have using this kind of models. So if you understand very well, if you understand your problem, you can apply, so if basically on the dimensionality aspect of the bias, you can apply these models very effectively. Otherwise, you cannot have great advantages with respect to real valued neural networks. With respect to the second question, it was
statistics.
The statistics. Yeah.
Yes.
Also for the kind of statistics, there are lots of properties, because you can consider also high-dimensional statistics. For the quaternion part, they also these kind of algebras are equipped with very nice properties with correlations and the correlation matrix, and also the statistics of higher order. And there are some, for instance, it is very nice. We defined a lot of, I don't know, work also based on the correlation matrix, like the redefining the KL divergence and using a lot of statistic properties in the quaternion domain. They are very, very nice also to consider some kind of properties, and so in that sense you can have to consider some properties also of the signals, if they are circular, non-circular. So you can have two kind of correlation properties, so you can have a simplified correlation in which you just consider the main diagonal in the correlation matrix, or you can consider the whole correlation matrix. There are a lot of nice things also from the statistical points of view. I think these are very nice also to explore that part.
I mean, those students will probably have some questions. So a simple extension, or a simple case of is when you have 2, which is a complex number, right? A complex number. We don't see very much use of complex number in the neural networks.
Yeah.
Yeah, it's all real. Right? Maybe in communications.
Yeah.
You know, this is very good. In terms of in neural network, you don't really go into the Fourier domain.
Yeah.
You don't use. I mean,
Yeah.
audio in a Fourier domain is very, very, you know, it's important. Yes, right. So, but you're saying that if we go to dimension of 4, 8, we make in some more things.
Yeah.
And, I think
That is very, very interesting because you can exploit the dimensionality of, and nowadays we can process a lot of data sets which are based on multimodal data or multidimensional. So it is very easy to find data which are built in this way.
Yes, that's right. Can we take some questions from the students? Any questions?
So thank you for your talk, and I have a question. So this is the first time I heard about the hypercomplex for the deep neural network, so which is very novel. In your presentation, you say that the step to do the hypercomplex thing on neural network is that you project from the real value domain into the hypercomplex domain, and then somehow you project back into the real domain, and you perform some optimization flow to learn about the neural network. So could you explain a little bit more detail how to project it into the
no. So let me say so. So this kind of projection is actually very, very easy in the sense that basically if you have a multi-channel or multi-dimensional signal, you can just take each channel and consider each channel as a component of the quaternion. So basically when you build your hypercomplex or quaternion signals, you can say that, I don't know, the first channel is the channel 0 of the real part of the hypercomplex and so on. So basically you are just considering, so it is not a real projection, but it is just a consider of each channel as a component of the hypercomplex domain. Once you make this part, you have built the hypercomplex signal, and you can process, you can pass the hypercomplex signal to the deep learning model. From a point of view of the implementation, this happens very, very easily. So it is more easy than making all these kind of hypercomplex embedding and so on, because you can just deal with real value numbers. So once you define the Hamilton product in the sense that you know the position of the parameters that are shared, and basically you build you redefine the multiplication. So the only operation that you need to implement is the redefinition of the multiplication. Once you redefine the multiplication, you can treat the multidimensional signal as a matrix or a tensor and so on. Okay, so it is, you just focus on real valued values. So basically this step can be also from a point of view of the implementation can be skipped. So you just redefine the multiplication, and so instead of using a classic multiplication in your network, you use the Hamilton product for quaternion convolution. So of course we built during the years we built a library, and so it is very easy to implement some kind of networks like this one. You need just to change the operation of the convolution with the same call of the quaternion convolution, for instance, but at the end you just need to do that. Inside you have the redefinition of the multiplication following the Hamilton product. But from that sense, it is like having, instead of processing step by step these signals, you can have a processing of a signal which is hypercomplex, so that can be represented in, let me say, instead of just using view individual channels, you can see a signal in a 3D space, for instance, directly. So it is like a way to having a different space, or just in the domain of the input signal.
So, it's like having you're constraining the parameters of the filter in the Demystifying network, and the operation that you can have, right?
Yeah.
So you're fixing the filter in a certain way, so that the parameters are set in a certain way, and when you do some operation, you get. So that's the inductive bias that you are talking about, right?
Yeah.
So.
So you can have the same process as a real valued network. So it is the same. The only thing that changed that we redefined the layer and the multiplication, basically.
Now I'm just wondering if there are toolbox that would allow you to do this operation very easily in maybe PyTorch. Are there tools?
We developed a library in PyTorch in order to do this very easy.
Various things, I see.
Yeah, and so I didn't write the link, but of course we have. So I don't know, is the master of PyTorch of developing the layers of hypercomplex.
So we would have a library that we could put, and then
so instead
very easily gradient descending will just that's good.
Yeah, instead of using I don't know, the classic convolution you have, and the convolutional layer, you have the quaternion convolutional layer, but you can use it similarly the same way. So you have just a redefinition of the multiplication inside.
So in terms of performance, in terms of performance, in what particular task this would perform better than all the state-of-the-art there's many, there's you showed CFAR, ImageNet detection, there's audio detection, there's transfer, there are many different tasks using hypercomplex. What does maybe come best?
Of course. The best way is when you have problems in which there are some information that is shared among the channels, and it is difficult to find if you process only channel by channel. Okay, for instance, in the last one of the last examples I showed you for the breast cancer analysis, hypercomplex models perform very well with respect to. So I didn't put some numerical values, but you can find all the numerical accuracy in the paper. But actually, this fact is very interesting, because if you process image by image, it is difficult to understand all the things that happens inside the data. While here you have a complete view. And this, of course, is a very nice example, because you have some kind of information that can be correlated among channels. Okay, so you have some kind of information that is that is some kind of interaction between channels, and of course in this case it is very good to use this kind of models because they can easily find some good performance, provide some good performance with respect to classic networks. For a classic classification, for instance, if you don't have any particular prior knowledge about the problem and you need just to have a classification, of course you will not have so great accuracy. Maybe the great accuracy may be due to the fact that you are using, I don't know, large networks, and you can have some regularization, some reduction of the overfitting by using less parameters. And so this can be one of the advantages that you can have. Otherwise, you will not have a great advantage in terms of accuracy.
I think that great advantages may come in the case of data or applications that are generated from, let me say, a non-physical process, such as the 3D audio case or 3D scenarios where you can leverage the multi-hypercomplex representation to build a more proper representation of the space or of the physical process that generates the data. So when you grow in the space or in complexity of the representation, I guess I believe that hypercomplex models.
Also, in the case of post-estimation, it is very nice because here it is an example in which you can exploit very good the rotation and translation of the data inside the data, and so these are aspects that are very that are grasped very well by this kind of networks. So if you have other applications which you need to perform rotations on translation of the data, probably this kind of methods will provide some very good results.
I completely agree with her, what you said about providing better representation, more diverse representation about it, because deep learning is about representation, and I'm thinking maybe this is good for out of distribution detection, not for normal things, but out of something that cannot be detected, or maybe also good for adversarial attacks, because it's it can be robust, and also it can provide a multi-view, different view of providing different representations. So I think there's a lot of work that can be accomplished with this work.
Of course, if you are interested, we can have collaborations.
Yes.
If also any one of you are interested in trying this kind of methods, we can give you, of course, support or any information you need.
Wonderful, wonderful. Thank you very much, and we will pass this on to the department, and I think you will get a lot of people interested in your wonderful work here. I think this is this is the first time that I've seen this, and I think it's great. Yes. Yes.
So if you want, I have also some slides just to say the things we do in our lab.
Sure. Can you show us? I mean,
Also, apart from this hypercomplex stuff. But just a brief introduction to.
Tomorrow I'll show you what we are doing.
Okay.
So maybe,
yeah. So it is just some kind of topics if you are interested in possible collaboration. So this is the our research lab. So basically, there's me, Eleonora, and other guys. So our lab is, so basically we have some kind of different research area, but all dealing with deep learning models and.
That's Vatican, right?
Yeah. It's it's
I didn't get to go. Oops, sorry.
And so for the part of quaternion and hypercomplex bias, it is something that we are working on. So like build hypercomplex bias in neural networks, demonstrate and prove some bias, and also test in some real-world applications. This is actually something that on which we are working continuously. We are working a lot also on with generative models. So basically on solving inverse problems with generative models, with audio, image, like super resolution, reconstruction, in painting, all these kind of problems. So this is just something that we implemented for inverse problems in a communication scenario. So we have some kind of signal, and we want to reconstruct on the other end based on some in painting, basically. So we are interested in a lot of this problem, so dealing with generative models. Also, we are interested in integrating some kind of signal processing techniques in generative models. For instance, we are working with a PhD student with using wavelets in diffusion models, for instance. And so all the parts of wavelet signal processing can be introduced in diffusion models. And it is also something that is done in the literature, so there are also some other papers in this area. So basically, it is just an example of how to deal with wavelet transformation and deal with generation with diffusion models. So we are interested also in exploring this kind of areas. Other topics, basically, we have some kind of, so in the last year we proposed some challenges, basically at ICAST for other conferences like this, on 3D audio sources. So we record the data, and we can have different tasks on 3D audio. We are having some research in explainability in generative deep learning, also conditional generation for super resolution, other kind of generative models for something related to metamaterials or AI design, so also architectural design, something like this. Generative AI for health is also something on which we are very interested, and efficient models that we can apply, of course, in a lot of situations. So basically, these are some possible topics on which
we're in sync. We're in alignment.
Yeah, great.
Because we have many of our students are working on generative models, not only for images but for text.
Yeah.
We're doing image text, multimodal. Wow. So I hope some of our students will show you some interesting demos tomorrow in the morning. Okay? Okay, so I think well, we end here. I think this is just, I mean, I don't think I can go to sleep today because it's just fantastic. Thank you so much. I thank all the students for coming here. I think it's wonderful. Tomorrow, I hope we have a chance to show our guests what we've been doing with our editing, with diffusion. We've been working with diffusion model a lot.
Great.
So, and we've also worked with text, so chatbots and multimodal things. We also do a lot of 3D segmentations and various work. So if it's not too difficult, can we see all of you tomorrow morning? Our students are sort of phase shifted. So they work at night and they come to lab in the afternoon. But anything else?
Yeah, we have the same problem.
Okay, thank you very much for coming, and I'll see you guys tomorrow morning. Okay, great. Thank you.
Thank you.
Let's give our
Thank you.
wonderful.